Bismillahirrahmanirrahim. Assalamu alaikum and a very good morning to all of you. It is my great honor and privilege to welcome you all to today's workshop titled Innovations in Precision Agriculture, Remote Sensing for Smart Crop Management. Let's begin by seeking the blessings of Allah Almighty through the recitation of the Holy Quran. Thank you all for being here today. As we move forward with our workshop, it's important to get a comprehensive understanding of the institutions and labs deriving innovations in artificial intelligence and data science. To provide us with an introduction to School of Electrical Engineering and Computer Sciences and the Machine Visions and Intelligent Systems Lab, I would like to invite Dr. Fahad Ahmed Sati to the stage. Dr. Fahad Ahmed Sati is an assistant professor specializing in artificial intelligence and data science. His extensive expertise and research work has significantly contributed to the growth of these fields at SEECS and the MachVIS lab. He continues to play a key role in advancing the research. We are excited to have him share more about these pioneering platforms. Please join me in welcoming Dr. Fahad Ahmed Sati to the stage.
Hello all. I will try to keep it short. Ladies and gentlemen, distinguished guests and esteemed colleagues, it is with great pleasure that I will introduce National University of Sciences and Technology School of Electrical Engineering and Computer Science, only known as NUST SEECS to you. So, established over 2 decades ago, in 1999, it's almost about 25 years now, NUST SEECS has grown to be a cornerstone of technological education and research in Pakistan, with over 2,000 actively enrolled students and 200 faculty members. At NUST SEECS, we are committed to fostering an environment where theoretical knowledge meets practical application. As a result, we have a graduate employment rate of over 90% within the first 6 months of their graduation. And this is through the efforts of the faculty of the institution in order to impart both research-oriented and practical-oriented content to the students. Across undergraduate and postgraduate programs, we have over 100 different courses, and all of these courses contribute to how we build the students up from ground. We have over 500 publications in just the last 5 years. And if we talk about just the MachVIS lab, which is one of the premier lab of NUST SEECS, we have lots of students already in here, about 24 students. 6 of them are research assistants, 6 of them are PhD students, and then 12 MS students. We have lots of undergraduate students as well. And the success of this particular lab can be, you can see the success of this particular lab by looking at the projects that we have completed. Over the years, we have completed several MS, UG, and PhD projects, all with an aim for improving the livelihoods of the general population in Pakistan and beyond. We aim to create sustainable products. We aim to do sustainable research, and the result of this particular effort is over 120 publications in very good journals, about 60 publications in very good journals. We have several book chapters, several conferences, premier conferences. We have active collaborations with RR Lab, RPTU, Germany, Kingston University, London as well. Then we have good collaborations with Harvard Medical School, University of Warwick, Alan Turing Institute, and many other institutes across the world. We have also won several awards. Most recently, we won the ICESCO Chair for AI in Business and Finance. Dr. Moazzam Faraz is the main ICESCO chair for AI in Business and Finance. We have also Rutherford Fellowship from the Alan Turing Institute, which Dr. Mozam Faraz won as well. We have lots of local partners, lots of international partners. Overall, as per the aim of this particular lab, where we want to create sustainable products, and we want to work on sustainable projects which can also, contribute to research as well. We have produced several products which are being utilized by the Pakistan Agriculture Research Council and other areas as well. Our area of research includes precision agriculture, healthcare, especially smart healthcare, and then we also are working on multimodal knowledge graphs and computer vision and several other areas as well. So generally speaking, we are not bound to only one area, as long as we can, or you can think of one sustainable project that can help the community. You're always welcome to come in and talk to us, and we can see how we can realize your ideas into sustainable products. Okay. I think without further ado, I'll just finish the talk. I'll welcome Professor Berns, and we'll continue on with the workshop. Okay. Thank you very much.
Thank you so much, Dr. Fahad Al-Masaki, for that insightful information to SEECS and the MachVIS lab. We truly appreciate you sharing your valuable insights with us today. Ladies and gentlemen, today's workshop comes at a time when precision agriculture is becoming more essential than ever. With increasing global food demands and the growing need to address environmental challenges, modern agriculture requires smarter, more efficient technologies. This workshop focuses on one of the most exciting areas in agriculture, the use of remote sensing technologies to enhance crop management and decision making. Over the course of today's workshop, we will explore the practical applications of technologies such as multispectral, hyperspectral, and thermal imaging, combined with satellite, UAV, and the IoT data integration. These tools allow us to monitor crop health in real time, detect diseases early, manage water stress, and optimize resource use, all of which are crucial for sustainable farming practices. We are fortunate to have some of the foremost experts in this field here with us today, and it is my pleasure to introduce our esteemed lineup of speakers who will guide us through the latest innovations and advancement in precision agriculture. To start off our session, it is my pleasure to welcome Professor Dr. Karsten Berns, the Head of Robotics Research Lab at RPTU Kaiserslautern, Germany. Professor Berns will be presenting a case study on robotics in agriculture. Professor Berns is a professor of computer science at RPTU Kaiserslautern. He earned his doctorate in 1994 for his work on neural networks for controlling a six-legged walking machine. As a head of IDS department at the Research Center for Information Technology, he explored adaptive control for service robots. Since 2003, he has been a full professor at RPTU Kaiserslautern. He is currently heading the Robotics Research Lab at RPTU Kaiserslautern. His lab research focuses on developing reliable autonomous robotic systems, including middleware and controlling architectures for off-road robotics, humanoid robots, and biological-inspired bipeds. Professor Berns is an active reviewer and editor for the journals like Robotics and Autonomous Systems, and he holds leadership positions in various professional organizations including German Robotics Association and the IEEE. He has also served as the Dean of Computer Science at the University of Kaiserslautern. His pioneering work in agriculture robotics has provided innovative solutions to optimize farming operations through automation. Please join me in welcoming Dr. Karsten Berns to the stage.
So, good morning everybody, ladies and gentlemen. It's a big pleasure for me to be here again. I don't know, it's sixth time I'm here at NUST. I started a very long time ago, 2014 I expect. And today I pick a topic which is of course relevant in our group. This is how we really can make machines, robots, able more or less to make automation in farming processes. And you see the robot, and I will talk very soon a little bit more about it, what is relevant and how we proceed. First of all, I'd like to give you a short introduction to our group, what you will not see. These are the activities in the range of humanoid robot. We are also active here. We have switch off the sound. We have focused here on interaction, a natural interaction between humanoid robot and humans in a typical natural environment, so you can talk to the system. And the most important thing, because we are robotic guys, we like to have a natural body language. So the robot should more or less use mimics. So those have mimics as a back projection. This is artificial skin what is used to express also emotional states, to give more or less feedback loops with, for example, your mimics. You have hand gestures which you can use in addition, and of course you have to understand in the actual partner on the other side, so we make a lot of sensor processing to detect, for example, emotional state, what personality exists and so on. So here knows this better, so he has done his PhD on the left machine 3 years ago. We are, as I said, very active also in this area. The biggest part of our group is dealing with robots, mobile robots, for different application areas. You see here the application areas. We have some machines which are test machines, not very dedicated to specific application. But we have the transport application, where we have, for example, our MachVIS, which we have permanently optimized for. Here the Unimog is a truck-sized vehicle which can go in very rough terrain, make transportation tasks. And then the two biggest area where we are focusing on is the agriculture area, we will say more about it, and the construction side. Agriculture and construction is close to each other from our view. This is interesting that a lot of tools, methodologies, control concept can be used in both machines. So also directly, if you look to the application, what you have to do is really similar. That's why we can do this. And we were in the past also active in rescue operation, for example, for flooded environments. We develop a boat, or for rescue missions after earthquake. We built also a mobile machine with an arm which can take away parts of concrete and so on. So let's jump to the agriculture, and of course this is what we really like all to reach somewhere in smart, or you can also call it autonomous farming, which means at the end we like to have nearly no human in the loop. And this comes mainly in our region, for example Germany or Western Europe, US, that you have not enough workers to do in future the work. This is even now the case. We have big problems, for example, our wine production. We are very good in Rhineland-Palatinate, so the state where we are, and export a lot of things in the world. But we have not workers now on the fields who do this typical physical work. And now we have to rethink how also such things can be done by machines. And this is not all. How we can have an ecosystem at the end where all these components can somehow be merged together. So we like to have, for example, drones who make first inspection, look for whatever diseases on on the field, or you have also drones for spraying. We have then transport systems, we have systems which maybe do the spraying or other manipulation tasks, but you have also a digital system around. This is also important to understand, because you have a lot of information which you can use. For example, the weather condition, what the weather, of course, in the next 2 hours is, how you can plan whatever you like to do on the field. If you are finished, normally in Germany, I don't know how it is here, we have to protocol everything what we have done. For example, if you spray something on the field, you have to say at the end to a database that on this day we spray this liquid and so long and whatever. So this is what all these guys have also to do in addition, and also we like to automate such processes. That, as I said in the beginning, no human must really be in the loop. But this is a long way, and we are focusing from our group mainly on the machines itself. We make also a lot of activities. Hopefully later on Jakob will give us a talk about this detection, where we make also classification tasks on the field and so on. I will focus here on really the machines, how we can automate the machines. And you see here a few of our, one more, of our prototype machines, what we use, and they are totally different. So on one hand side, for example, look for the right video where we built a prototype for vineyard, and we have in Rhineland-Palatinate very steep slopes, up to 70%. Even if you like to walk up, it's very hard to do this. And here, of course, we built really the machine from the mechanical point of view to the electronics, the embedded system by ourselves. On the other hand side, you see, for example, this nice John Deere tractor where we have a cooperation, John Deere in Kaiserslautern. And here we have to add to their system whatever we like to do. For example, if we like to have a pattern recognition or a specific control or whatever. So we have to use as sub-components their system, because we cannot rebuild the tractor. This is impossible. So our systems must also be adequate to manage everything, not only building, say, prototypes where you are totally open to do it. And of course, I like to show you more or less the process with this autonomous tractor, what we have developed now in the last 2 years inside a bigger project. The task when we start, where that you have a tractor like a manual driven tractor where you can do the typical task what you should do on the field, for example, inspection of plants, detection of soil characteristic, for example, with ground penetrating radar, performing work processes like sowing, spraying, verticizing, mulching, mowing, all these typical things what you should do should be done in an autonomous way. Transport services, of course, is also a typical application what such tractors do manual at the moment. And our view was from the beginning that we should really have a system which allows also the transfer between the whole farm where the tractor is and the field. And this is hard in Germany because normally we have small farms and everywhere are streets in between. So you have to also drive over normal streets, which is by law not so easy. And of course you also have to take care that nothing happens. Then telecontrol is of course always an interesting point because it will take a little bit longer than really these systems will fully autonomously work. So what we like to have is that a human operator, maybe sitting in his office, from time to time can have a look what the system is doing. Maybe if the system comes, say, to that end, that you can interact with the system and say, oh yeah, you can go ahead or drive backwards or whatever you give as a command as a human. This has also an advantage that you, by law, have then also to guarantee that the system is safe. So you are responsible, not the controller, not the technical product. What we do and why we do it, we select this small tractor. not a big one, because we said we like to have a compact one to make a lot of experiments, also in restricted areas. We have not only big fields around, so where we can test. So we select this John Deere machine, which is 3 meter 1.8 in width and around 2.33 meter in height, 49 kilos weight. We have everything. This is the nice thing with this tractor. That's why we also have selected it. What is needed for these implements, what you can buy on the market. So everything what you have for big tractors can also be in another version, of course, a smaller version, be attached here. So we can also do every test operation what normally big tractors also doing. There are a lot of implements what you can buy on the market. Of course, also we can do this by ourselves. And it has also some electronic things where we can start to bring our controller here on the machine to control the hydraulic system. So what we have to do as an extension, and this is a big problem at the moment if you start with a real product. We have, for example, to bring somehow our electronics, our embedded electronics in, as well as the computing part. And of course we need a lot because we have a camera system, you see it later on laser scanner. You have a lot of processing to do, so of course you need powerful computing hardware which is not existing. So then we have no steering system. So this was another company who built it in. It's an hydraulic steering system, but we have also to operate this later on, so we have to write all the protocols to steer the vehicle. Then the most important thing is here. If you make a test vehicle, you should be able to stop the machine at every time. So you need an emergency system. And the emergency system also, if you like to have later on a product out of it, you have to implement it in a way that if everything is not working anymore, it has to stop. Which looks first of all simple, but it's not so simple. Because, for example, think about the battery is over and or a wire is disconnected, and now your computing unit cannot do anything. So in this situation, of course, the system has to stop, which means that your brakes must be active if they are open, and if the current goes away, it's directly closing. This is what you have to guarantee, and of course you have to activate it in a specific way. Oh, the other things are standard things. Of course, we have to control the speed. We have in front and in the backside lifters what we like to control. So we have to implement closed loop control also. Then, as I said, the computer architecture and the sensor system is what you definitely have to add to such a machine. And this is more or less what comes out according to the sensor system. We have here this a lot of different aspects what we have to implement. This is, for example, for the safety. We bought a specific SEECS outdoor laser scanner for safety application. And we have here wireless emergency stop, as well as everywhere buttons where you can stop the machine. This is, as I said, extremely important. For localization, we have the standard things, what we have on all robots, GPS, IMU, autometry, what we can use for navigation. We have 3D LiDAR, we have a stereo camera system, or 2 stereo camera systems on board. One in the front, this is the better one, which can look also a little bit more in the distance, and we have a second one, if you like to make navigation backward. This is restricted to the range, maybe you can see the next 5 meters. This is only if you like to go slowly backward. Then for remote control, we install a 360-degree camera where with a remote joystick you can do this, and for inspection we have typical ground penetrating radar, multispectral cameras and thermal cameras on board, what we have also tested in other systems. The computing architecture, this is the, as I said, the next thing what you have to have in mind. How do you bring a powerful computing system in? And this is an architecture what we have developed in the group, which is scalable. So here we have only an embedded PC, this part. The powerful PC, embedded PC means that it is more robust. You cannot put a normal PC in. After whatever, 1 day, it is defective. Because based on the vibration, you will destroy the boards. So this is what we think will happen. So you need specific hardware, and you can, this is the nice height. You have some own battery. This is also important because otherwise, if you use more or less the electricity of the tractor, of course you have a battery on the tractor, it could be that in between the current is not adequate, the voltage is not adequate, and then you have a reset of the controllers. So, and you normally have to spread it. The battery is bigger than we need. So I think we can run this for 1 day, and the battery will not be over than what we have or what we need. Then we have a GPU on it for processing tasks. We have also FPGA for stereo vision is directly installed in the camera. So the whole pre-processing of the stereo process is done here, which helps. Otherwise, we have to add more computing hardware. We have communication with 5G and with WLAN access points, which we can use to communicate. This is also important for testing. And of course, this SEECS, say a few words later on, safety hardware, which should guarantee that in specific situation, at least the machine will stop, will not go ahead automatically. You will have no influence. So, and then we have some remote links to control the machine and also remote emergency system. How can you do this with these emergency stops? This is extremely important, as I said. This is done with a so-called safety chain. It's a very primitive principle. You have a wire, and the wire runs around to every unit. And if you cut somewhere, with a switch for example, the wire, no current can flow, and then you have a drop down, and this leads more or less to specific activities. For example, the brake is closed, and you have no influence on it. So if you open more or less the safety chain, whoop, the tractor will stop. And this is nice to have a very simple concept to trigger this. The only problem is now who should trigger it, and in which way, which components. And therefore, of course, you have these emergency switches, these are simple, but also this laser scanner. And this laser safety scanner are done in a way that you define zones. Say, on this side, object should not come closer than, with a specific speed of the tractor, not closer than 40 centimeter. In the front, maybe 1 meter or whatever, and then I stop it. And then the higher level of control can do whatever it likes to do, but the machine will stop. We have separated system to guarantee the safety of such a machine. And this is how we hope that really it is safe. Of course, also here something can happen. And therefore we have a new hydraulic brake integrated into the system that have the features that if no current is there, whoop, the brake is closed by the hydraulic brake. This is what at the end happens. Now coming away from the embedded system to the development concept, how we build our software concept, how we also test our system. And these are always these 3 steps more or less what we do with all our machines, what you see at the beginning on this slide. So we first of all model somehow the operational environment in which more or less the machine should do whatever. So here we should be precise depending on the task what we like to do here in the simulation system. For example, if you drive on rough terrain and maybe you like to have a very precise description of the surface on which you are driving. We can do this if it should be really precise. You see this here with laser scanner measurement or stereo camera systems. We have an ICP implementation where we stitch more or less the points together at the end and get a very dense representation of the root environment. And this leads that you have a really nice, for example, representation of the surface, what is really outside. So we drive really over the test environment, protocol this data, distance data, make models out of that and use the models to put it in our simulation system. The rest of the simulation system, we use here the Unreal engine, is of course done by ourselves. Of course you need a tractor, you have to model the tractor in the simulation system in a realistic way. So not only the appearance is relevant, more relevant is, for example, the width of the wheel, the sizes of the wheel, all these kinematic parameters, otherwise you are far away from the real system and it makes no sense. So here we can start, we have also a tool chain from a CAD model of, a primitive CAD model of the vehicle. Not what the companies do, so not every screw or whatever is interesting for us, more or less the basic things, where are the axis, the width, the size, how is the turning angle, for example, of the steering, here this is Ackermann steered vehicle, and then this is relevant and this is what we collect, that model inside the system. And then the next big part is coming, we have also to model the sensor system in the correct way. Because at the end we like to exchange the controller, which gets some vision data or whatever, which runs here in the simulation with the real vehicle. So our software at the end, which controls everything, which makes the perception, should not be changed. It should be the same. Otherwise we implement again. This makes no sense. So we have to guarantee that from the qualitative point of view, this processing is the same. This is important. It's not important, for example, make the example of an image. It's not important if I have here a simulated image of the world and I compare it with a real image of the world. It's not important that the frequencies in this image are different. What you find out, for example, we have done this analysis, that if you have here simulation, you have not so many frequencies as in the real world. But if at the end, the decision what is taken out of whatever we see and whatever feature we extract is the same, then we can use it. Must not be, that's why we said the quality of the images must be the same, not really, well, intensity or whatever, brightness, the frequency, which is more or less measured with the camera. And at the end, we transport it to the real vehicle, and then we make experiments. Of course, on the real vehicle, we have to adapt. It's not without adaptation, we can forget it. But if the main things are working, this process is much faster. And of course, it's not a risk to do this in this way. So if you look once back to you see here the different parts, what we have to do. For example, as I said, the landscape, this is the landscape of our test farm, with the fields, can be generated based on real laser measurements, or in our case, we take cadastral data, which are very precise in Germany. So we have a resolution of 1 to 1 meter, which is normally enough to describe the surface in adequate way for our tests. Then, as I said, we have to model the tractor. You see it here. We model the full farm. Where are the fields? Where are the houses? What is the shape of the houses? Whatever we need, we can model this. Again, we have tools that this is not so hard anymore as before. And of course, what we also have to model is the field.